Examples of Lagrangian multiplier method. So if you remember, we did theory of Lagrangian multiplier in the last recording, right? We did some interpretation of the constrained minimization. I won't say interpretation, but the intuition behind the constrained maximization or constrained minimization. So let us look at few examples for Lagrangian method, right? Guys, this is going to be our bread and butter in the micro course. We will be either maximizing or minimizing. And since we are doing economics course, resources are always a constraint. So there will always be a constraint. They can be the constraint in terms of my income. So I'm the consumer. I want to maximize my utility, but I'm constrained by my income. I'm the producer, but I am constrained by the government quota, let's say, that government says you can't produce more than this. Or I am the producer. I want to produce a certain level of output, but I am what I want to do is that I want to minimize my expenditure, minimize my cost. So although I want to minimize my cost, subject to the constraint that I want to produce this level of output. So these examples are going to give you some cookbook procedure for the Lagrange multiplier method. Again, I am only doing that much which is required for my micro course. That's it, right? So don't think it's a complete class on the Lagrange multiplier, but this will give you very good overview of how the method works using few examples, right? So after this, I think you are well acquainted with certain level of maths which is required in the micro course. Again, I'm telling you, this is a work in progress. We'll be adding things later on, but after this, I'm sure you can start reading up books easily and you will start making sense of it. So you know by now how do you optimize for the one variable, for how do you find out the unconstrained optimization for several variables, constrained optimization for several variables. This is what it is. So it's not a complete maths class, but it is going to. I'm sorry, I took a lot of your time. So you have example 1 beta. I could have been interested in maximizing u is equal to xy. This is my utility subject to p1x plus p2y equals to m. p1x plus p2y equals to m. So this is what my objective is. And this is what my constraint is. Using Lagrangian technique. So if you remember, we did this. You'll be writing your function this way. Lagrangian is f, this is your objective function, plus lambda, this g, right? So I can write my constraint in this way. It's to 0. So what do I have is I'll set up the Lagrange. My objective xy plus lambda m minus p1x minus p2y, m minus p1x minus p2y. How many partial derivatives you need to find out? So in case if this would have been the unconstrained problem, so beta, what is it that I would have found out? Always whenever you are studying, try to make connections in your head. You would have found out du by dx equal to 0, du by dy equal to 0. I mean, basically, in case if you just have the function like this, right? So del f by del x equals to 0, del f by del y equal to 0. This is what you said now when you were doing the unconstrained optimization. Right here. This is what you said, y equals to f of x1, x2, and so on to xn. And you said that for the unconstrained optimization, you try to do this. You have n equations in n variables, and you try to find that out. Here, how many derivatives you need to find out? One for each variable, x and y, and one for the constraint. So this lambda is also the variable now. We'll be treating that. So del L by del X is Y minus lambda P1 equals to 0. Del L by del Y is X minus lambda P2 equals to 0. And del L by del lambda is M minus P1X minus P2Y equals to 0. And you know now that all of them, they have to be solved simultaneously, right? They have to be solved simultaneously. So it is what? You divide one by 2. So it is Y by X equals to P1 by P2, Y equals to X P1 by P2, and you substitute this Y back into the third constraint. In place of Y, you guys can write X P1 P2. And then you can write it as M equals to 2P1X. So X star equals to M by 2P1. So this is the function of income and prices, right? The moment you have X star with you, you can find out Y star. What will that be? X star into P1 by P2. But this is P1 by P2. In place of X star, I can write M by 2P1. So my answer is Y star is M by 2P2. Y star is M by 2P2. You with me? So what are the optimals? X star is M by 2P1. Y star is M by 2P2. This much. Okay. Beta, if I would have, now some of you might think that this is repetitive, but let me remind you again, this is the part of the very basic course, right? So I need to be little repetitive and I need to do all of this for my own satisfaction, that I have done this, I have put this on the channel and people can understand this and people are benefited from this. So you want to maximize this subject to. So this needs to be done, although this is little repetitive, but I'm going to make a point after this. So this is the part of the basic course beta. So this has to be done. I'll set up the Lagrange. I'll write my objective function. I'll write my constraint. So I've written my constraint as this. I've written my constraint like this, na beta. So del L by del X is alpha X to the power alpha minus 1, Y to the power beta minus lambda P1 equals to 0. Del L by del Y is X to the power alpha beta Y to the power beta minus 1 minus lambda P2 equals to 0. And beta, divide first by second. So you have what? Alpha X to the power alpha minus 1 Y to the power beta upon X to the power alpha. You have beta Y to the power beta minus 1 P1 by P2. So I can write this as alpha upon beta. So this is going to be what? Your Y to the power beta minus 1 minus beta minus 1. So that is minus beta plus 1 whole upon X to the power alpha minus alpha minus 1, so it is minus alpha plus 1 equals to this. So it is alpha upon beta. Beta. This will get cancelled out now. Your y upon x equals to p1 by p2. So y equals to beta by alpha x p1 by p2. And I'll be substituting this y back into the constraint. In place of y, I can write beta by alpha x p1 by p2. So you have what? Alpha m minus alpha p1x minus beta p1x equals to 0. So it is alpha m equals to x into alpha plus beta p1. So beta, what is your x star? Alpha upon alpha plus beta m upon p1. What is your y star? Beta upon alpha p1 upon p2. In place of x star, I can write alpha upon plus beta m upon p1. So this alpha will get cancelled out. And this p1 will get cancelled out. Your y star is so this is the demand function for y. Now, acha, what is the share, or what is the, you'll say, share of expenditure on x in total expenditure? So let me write that as S1 or SX or whatever. That is share of X in the total expenditure. How much expenditure you're making on X, beta? P1X star. What is the total expenditure? Total expenditure is M, because expenditure is equal to income. No? So it is P1 by M. How much of X star you're consuming? This much. Alpha upon alpha plus beta M upon P1. M cancelled. This thing cancelled. So the share of X in total expenditure is alpha upon alpha plus beta. Right? Similarly, share of expenditure on X, expenditure on Y, in total expenditure is going to be P2 Y star upon M. So P2 upon M. What is Y star? Beta upon alpha plus beta into M upon P2. So that is beta upon alpha plus beta. So when you have the utility function like this, x to the power alpha, y to the power beta. So what is the share of expenditure on x? That is alpha upon alpha plus beta. Share of expenditure on y, that is beta upon alpha plus beta. One thing. Other thing, you have the utility function like this. From next time, when we want to write the demand function for X for such a complex utility function, you will be writing X star as alpha upon alpha plus beta m by p1. Y star as beta upon alpha plus beta m by p2. You have done a simpler case than this, which was this: u is equal to x into y, but that is x to the power 1, y to the power 1. So what is x star? 1 upon 1 plus 1. That is 1 is the power of x, 1 upon 1 plus 1 into m by p1. So this is what m by 2 p1. This is what you have also found out here, m by 2 p1. Similarly, y star is beta upon alpha plus beta. That is 1 upon 1 plus 1 m by p2. M by 2 p2. You with me? There is one more example. Let us do that. I need to now minimize E is equal to P1x plus P2y subject to U bar equals to x. So now I want to attain this level of utility. For this, I need to minimize this expenditure. So this has become my objective. And now this has become my constraint. So I'll set up the Lagrange, which is P1x plus P2y plus lambda U bar minus xy. So how many partial derivatives you will find out? 1 for x, 1 for y, 1 for lambda. Is P1 minus lambda y P2 minus lambda x equals to 0. U bar minus xy equals to 0. To divide 1 by 2, you'll be getting P1 by P2 equals to y by x. So y equals to x P1 by P2. I can substitute this y back into the third constraint. U bar equals to x square P1 by P2. So x square is P2 by P1 U bar. So x is root of P2 by P1 U bar. So if you want to minimize this expenditure, when you want to have this much level of utility, this is the level of x which you should be consuming. So the moment you have x with you, you can substitute this in y here. So it is what? X into P1 by P2. What is x? P2 by P1 U bar into P1 by P2. This is P1 by P2 U bar, root of P1 by P2 U bar, right? For your knowledge, the demand functions which you get from the expenditure minimization problem, those are called Hicksian demand function. And the demand functions which you were getting from the utility maximization problem, they were called Marshallian demand functions, right? So this is the simple rule for your Lagrange multiplier, right? This technique. This we are going to use extensively in the course. So the idea is that you're using the equality constraint problem. Uh, there are several things which are related to the constraint optimization, several more things, but I'm just trying to keep it as simple as I can, which you can use directly into examples and solving problems instead of going into theoretical complications, right? So this is what I wanted to do in this class. Thank you, Beta.